This is problem 8-1, and for part A we have to determine the charge Q naught on this sphere up here. Well, easy to do that by, since we know the voltage, we can just simply use the formula V equals KQ over R, because it's an isolated conducting sphere. An isolated conducting sphere, voltage is the same everywhere inside of the sphere. So we straight plug in values, substituting in the values given here, the radius A and the potential negative. So negative 2000 equals K times Q over 0.2, where K is the constant given in the reference sheet. It's like 9 times 10 to the negative 9 or something. And Q turns out to be negative 4.4 times 10 to the negative 8 coulombs. Alright, in part B, there we determine the radius of the magnitude of electrical field in the following regions as a function of distance r of the inner sphere. For this big sphere right here, part BI, the electric field is 0 because we're just looking at this inner sphere right here, and electric field inside a conducting sphere is always 0. And for part B double I, looking for A less than R less than B, so it would be A less than R less than B, so it's right here. So it's enclosing the sphere from part BI, so that we can use the formula E equals KQ over R squared to calculate electric field potential, because it's not inside the middle sphere anymore. This time we're looking at outside, so you can use KQ over R squared in this case, which in this case would turn out to be 9 times 10 to the 9 times 4.4 times 10 to the negative 8 over R squared as a function of R. So we have E as a function of R now. For part B triple I, B less than R less than C, it's inside this sphere right here, this thing right there. So it's inside the mouse sphere, so that's why it's 0. And for the radius bigger than C, the electrical field is 0. Right. So part C wants us to determine the potential of the magnitude of this. Determine the magnitude of the potential difference between the sphere and the conducting shell. So right here, the electric potential between here, V in here. In this case, since the electrical field does exist in between here, electrical potential, it does exist, so we can just straight up use the formula V equals negative integral from A to B E dot dr. We plug in the values, so for E from integral from A to B of Q naught over 4 pi epsilon naught, which also known as KQ over R. So integral from A to B of KQ over R squared. Since K and Q are constants, we can pull them out, so it becomes KQ integral A to B 1 over R squared, and then to simple calculus, if the answer turns out to be equals KQ times 1 over B minus 1 over A. And that would be potential where you would then plug in the values with k, 9 times 10 to the 9th. Then q would be the q not initially given. 1 over b minus 1 over a is the given here. B and A, and if you plug it in right, it should turn out to be 1,000 volts. Alright, in part 2 we have to find the capacitance of the spherical conductor. The spherical conductor is just C equals Q naught over V, and since we know the V we determined inside from part D, we can easily solve it since we just plug in the initial values, and it should give us an answer of 4.4 times 10 to negative 11 farads. And although it got cut off a little earlier, you can still see like the work derived and stuff. Like here's part D, like starting with the negative integral, then you do the calculus, you get kq over 1 times 1 over b minus a, which equals 1,000 volts. Then for part B4 it's 0 because electric field inside a sphere is 0, so yeah, it's no electric field.